Alright guys, yesterday I introduced solving trig equations, so really today my goal, as you may be able to see as you look at these notes, to kind of try to just go over all the different types of methods for solving trig equations, some of which I have kind of shown you already. I just want to really specify those. So that's really what the goal is today, is just to make sure you understand again every unique method for solving trig equations. So we're going to still stick to solving trig equations without a calculator at this point. I will kind of bring up little things with calculators and stuff as we go in through things. And also, since I'm not there today, you'll get an opportunity if you have any questions during our block period to ask those. So anyway, to get us going, we're going to go example A, and if you need to pause at any point, go ahead and do that to write these down. But the first one you'll see I have highlighted there in red. This is the method we're going to be using. Again, this first one, I did show this yesterday because we were kind of doing this a little bit, but we're going to solve by isolating trig expressions. Maybe I didn't go this route because the trig expression there's only one of them on the examples that I did yesterday, but anyway, what we have right here on this example is we have two trig expressions, and all I really want to do to get us started here is to isolate them so that you have the trig expression on one side and you have the number on the other side. So in order to do that here, I'm just going to go ahead and subtract tangent x from both sides of this equation. And notice there's only one tangent x, so 2 tangent x minus 1 tangent x is 1 tangent x. So we have tangent x minus radical 3 equals 0. So at this point, I'm now going to go ahead and add radical 3 to both sides. And you have tangent x equals radical 3. So before I really go through this, solving this and finding the angle and things like that, I do want to give you a little bit of a tip here working with tangent functions on the unit circle. So if you want to know this, then just go ahead and kind of make this little note for yourself. But I'm going to talk about this first quadrant and those main angles, those special ones right here. You got your 1, 0, you have your pi over 6, your pi over 4, your pi over 3, and your pi over 2. Those are those 4 points that I have listed. So these 4 points, you have the 1, 0, and you have the radical 3 over 2, 1/2, and so on. I want to kind of tell you real quick what all these angles are in terms of tangent. So I'm just writing the points up here so you understand each one that I'm going to be going over. And you can really go through all the points and do sine divided by cosine every time. That's really up to you. But again, these are your angles. So I'm going to start with the tangent of 0 radians or 0 degrees. It doesn't really matter. This one, again, remember, it's always sine over cosine. I'm not going to do this for every one because it gets kind of old, but this is going to be 0 over 1, which is 0. So again, the tangent of 0 radians is equal to 0, which makes sense because obviously, you can kind of see that. And then you're going to get the tangent. The next one is going to be pi over 6 radians, and now I'm dealing with this point right here. And what you want to know for this one, it is 1/2 divided by radical 3 over 2. But what I want you to start to get used to, because this happens enough where you want to know it, it's going to be radical 3 over 3. So that's what it actually equals. And again, I put these points up here because you can always kind of run through it. Just go like 1/2 divided by radical 3 over 2. You multiply, keep change, flip, and you can kind of see how these cancel, and if you rationalize, you get that. I just want you to kind of understand that, again, I want you to start to know these tangent values. And then you get to tangent of pi over 4. That's going to be radical 2 over 2 divided by radical 2 over 2, so that's going to equal 1. And then you get the tangent of pi over 3, and that's just going to be radical 3. So these are the two that students tend to have a hard time kind of getting straight. And notice the smaller angle is radical 3 over 3 because this is a smaller angle. It's actually a smaller output here. And then the bigger angle is just radical 3. You just lose the 3 on the bottom. So anyway, that's that one, and then the last one is tangent of pi over 2. And pi over 2, I can write this one out. It's 1 divided by 0, which is going to be undefined, which makes sense because that's where your vertical asymptote is located. So these are some good things to know. So I'll just kind of put them up here in the corner, and you can use them as you see it. Now again, sometimes obviously if you're dealing with cotangent or cosecant or secant, sometimes you just need to do the division here, and once you get the hang of all of them, maybe you start recognizing there are some patterns on those two. But it just gets to be kind of crazy. That's if you have to memorize everything. So you still want to know where it all comes from if you have to look them up. Okay. So in this case, I'm looking for tangent of x is radical 3. So when I'm looking at that one, I see my radical 3 is going to happen. That's at pi over 3 right over here. So this answer is going to be, my angle is going to be pi over 3. Now just understand when you're doing pi over 3 that this this angle, this output I should say, it happens one time within that period. So you can write your answer as pi over 3, and you can also go ahead and kind of write out all the answers as x equals pi over 3 plus pi k, if you're going to write it out as an equation. So that's going to be your options when you write your answers, depending on what you're asked for, and you can just kind of go from there. And lastly on this too, just so you know, if you want to get that answer from 0 to 2 pi, say I'm asking you for that, understand that this first angle that I found is pi over 3. So what you're going to do is you're going to take that's one of your answers, that's pi over 3. And then the other answer, you're basically adding pi k to it. You're adding pi. In other words, you're finding the next value along that period. So if you're going to add pi over 3 plus pi k, the other answer, the second answer, before I just write it, you're basically adding 3 pi over 3, because 3 pi over 3 is pi, so your other answer would be 4 pi over 3. Now if you think about it and you add pi again, you've actually gone around 2 pi, so you're going to be greater than that. It would be 7 pi over 3, which is greater than 2 pi. So these are going to be your two answers if I asked you to answer it only from 0 to 2 pi. So these are the two potential answers that I'll generally ask you for, depending on if I want all the values of theta or if I just want the values of theta from 0 to 2 pi. Okay, so that's going to be example 1. Now we're going to jump down here to example 2, which is solving by taking the square root of both sides. So if you're going to take the square root of both sides, the first thing you're going to want to do, and this is just like solving equations in algebra, you're going to want to isolate the squared term. So in this case, that means I'm going to subtract 4. And again, at this point too, if I'm going too fast, remember, pause the video, and you can and you'll be fine. So I'm going to subtract 4 from both sides. So I'm going to get 3 cotangent squared x equals 3. And then I'm going to divide both sides by 3. So you end up with cotangent squared x equals 1. Now the big thing on this, we are going to square root both sides now. This is that whole solving by taking the square root. So this is going to give me cotangent, but understand when you take the square root of both sides, you are going to get plus or minus. So I'm going to get plus or minus 1 for my right hand side. So I'm going to have two potential solutions that I need to make sure that I'm checking on this. So that's what I'm going to have to do on this. I'm going to check my my solutions, and you'll see as I do that, I'll use a little bit of that unit circle again. But because it's plus or minus 1, you should have a pretty good idea where those angles are located. So with cotangent, if I'm trying to find those angles, I know that one of those angles is going to occur at pi over 4. That's going to be that positive one, because pi over 4, when you look at that, that's going to be radical 2 over 2, radical 2 over 2. So I know I have that as an answer. I know I have x equals pi over 4. Now if I went around the whole circle, I'm trying to find all my answers from 0 to 2 pi, then I can do that, because if you look at it, the next answer is going to be over here at 3 pi over 4. Now if you're not sure why, again, understand all these points are going to occur when I have a radical 2 over 2 and a radical 2 over 2. As long as one of them is positive, well, it doesn't really matter. I have plus or minus 1 here. So as long as I have the same numbers for x and y, I'm going to get plus or minus 1 when I divide cosine and sine. So the next point is going to be my other 45-degree angle, which is at 5 pi over 4. And then I have another one here at 7 pi over 4. Now I wanted to write it out this way because we want all the answers from 0 to 2 pi. So if I'm asking for all those answers, we actually have 4 of them. So we have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So these are going to be all the answers, again, as I said, from 0 to 2 pi. And again, that's because those are all the points that have radical 2 over 2, radical 2 over 2. Because again, the sign doesn't matter here because it's plus or minus, so all of them would really work. If I did want to get the equation on this, one thing I want to note before I write the equation is notice that there's a gap of 90 degrees or pi over 2 radians between each of my answers. So there are a couple ways you can write this. You can literally put take each one of these answers and put a plus pi k next to it, which actually it would be a 2 pi k in the way I wrote it. Obviously these answers are going to repeat every 180 degrees or pi radians because that's the period of cotangent. But there's a quicker way. So again, the longer way is this. You can do this. You can go pi over 4 plus pi k, and then you can also go 3 pi over 4 plus pi k, because the pi over 4 is going to take care of these, because every time you go 180 degrees it's going to overlap with one of those two angles, and the 3 pi over 4 plus pi k would be that second set. So you may see the answer written like this. However, there is another way you can knock this out, and I want to make sure you're aware of that as well. And that goes back to where I was saying these angles differ by 90. So you could also say this: pi over 4 plus pi over 2k. And you'll notice again this angle, you see the first one is at pi over 4, and notice the difference between each of those answers, those solutions, is actually 90 degrees. So that's the common interval between all your answers. So again, a couple ways you can write that. Just make sure you understand how to find those angles and the method to get there. A lot of this again comes back to the unit circle. So that's solving by taking square roots of both sides. Okay. So the next set, as you'll see here, is going to be solving by factoring. Now we did already do some factoring. We were factoring trinomials on Monday. So this one I just did, it's a little different. This is not factoring trinomial. This is going to be factoring by GCFs. So with this one, again, when you're factoring, let's try to set this equal to 0 so we can use our zero product property. So if I was going to do this one, I'm going to go with minus 3 cosine x on both sides. And again, these don't combine, so try not to combine them because it's just not going to work. But there you go, cosine x sine x minus 3 cosine x equals 0. All right, so at this point, again, we want to pull out a common factor, which in this case is going to be a cosine. So you get cosine x on the outside, and this gives me sine x minus 3 on the inside. So you at this point just take each factor, set it equal to 0. So cosine x equals 0, and sine x minus 3 equals 0. And this should be familiar to what we did yesterday, where sine x is not going to equal 3. And if you remember, your sine function has an amplitude of 1. Therefore, the highest it's going to get is 1, unless I had a vertical shift, but then I would be moving that over anyway. But anyway, yeah, it's not going to work. So we cannot solve that factor, which just means there's no solution there. But I can solve when cosine is x. So I want to get all the answers from 0 to 2 pi. So if I'm doing that, again, we know the restriction normally, if you plug this into your calculator, it's only going to get you an answer from 0 to pi, but we know it actually occurs more than that. And again, cosine on your unit circle is the x value. So I'm going to look and find out all the times when my x value is equal to 0, and it's going to occur at these 2 points, at 0, 1 and 0, negative 1. I have the negative, there it is. Okay, so those angles, that's what I'm looking for. So those two angles are going to be pi over 2 and 3 pi over 2. So those are going to be your two solutions if I was asking you to find the solutions from 0 to 2 pi. Also, if I wanted you to find the equations, you would just say x equals pi over 2. Now you could go pi over 2 plus 2 pi k and 3 pi over 2 plus 2 pi k. But also be aware that the answer on this, notice it differs, or the gap between them is a straight line. So that would be 180 degrees or pi radians. So you could just go pi over 2 plus pi k. Again, that's where it's really nice to see how I draw the unit circle. I can see these patterns. Okay, now again, is it wrong to write it as two separate equations? No, it's not. You can go pi over 2 plus 2 pi k and 3 pi over 2 plus 2 pi k. Just also be aware that if you're going through this, say it's multiple choice, I'm taking a test, and you see that pi over 2 plus pi k, well that's correct. It means the same thing. Okay, so again, that's going to be solving by factoring. Again, I'm moving along here because you can always pause this, so I figure I can just keep going. Next up is going to be solving by rewriting using a single trig function. So that means in this case, you'll see the example I have, it has two trig functions in it, and we're going to go ahead and use a trig identity to simplify that down to one trig function, just make it a little bit easier hopefully. So if I do that, I'm going to take this 2 cosine squared x, I'm going to call it 2 1 minus sine squared x minus sine x minus 1 equals 0. So if you do a little bit of combining concepts here, I'm going to go 2 minus 2 sine squared x minus sine x minus 1 equals 0. And again, I'm just going to go ahead, I'm going to zoom in here so you can see it a little bit better as well. But this is going to be negative 2 sine squared x minus sine x, and then 2 minus 1 is plus 1. Okay, now if you don't like dealing with these negatives, you have a couple options. You can actually put the 1 first and these 2 sine squared last so that you have a positive to begin with. You can also just divide. There's a nice little trick here. You can divide both sides by negative 1. That works because 0 divided by negative 1 is 0 anyway. Or you can just move everything to the right hand side of the equation. As you can see from what I've drawn, I'm just going to divide both sides by negative 1. And that's going to give me 2 sine squared x plus sine x minus 1 equals 0. That's just the method I prefer. It's quickest. So, I like the quickest way to fix this thing up. Okay, but now I'm going to go ahead and factor this. This is a factoring problem. So we're getting our factoring problem in anyway. So this one, again, I'm not teaching how to factor at this point, but we have 2 sine x and sine x, and we have 1 times 1. And I just want to figure out how to get my signs worked out here so I get a plus 1 sine x, and that's going to happen with a minus and a plus. Because if you notice these two terms, that'd be a negative 1 sine, and this would be a positive 2 sine with my outside terms. So this is the proper factored form of that quadratic, it's not really a quadratic function, but the quadratic looking function. So at this point I can now take both factors and set it equal to 0. And it looks like both of these will actually be solvable. So I'm going to get sine x equals 1/2, and I'm going to get sine x equals negative 1. So we're going to take a look at our unit circle here, and I'm going to find all the times where sine either equals, I'm just going to get all my answers at once here. I want to find out when sine equals positive 1/2 and when does sine equal negative 1. Well, remember, these are your y values. Sine is your y value. So I have a 1/2 right here. So radical 3 over 2 1/2 at this point. I have 1 out here. I have negative radical 3 over 2 and then 1/2. And don't forget my negative 1, which is going to be right here at 0, negative 1. So again, I'm drawing this circle so you can kind of see here. And hopefully you kind of see a little bit of a pattern on this. If not, I'm going to try to map it out for you. Okay. You'll see I got these three answers. That last one, so I'm just going to do a dark line so you can kind of see it a little bit better. But you notice how it's kind of cut off into three equal segments? Well, here are your angles. Let's start there. Okay, your angles are going to be pi over 6. That's your first angle. So if I'm listing all my angles out, I got pi over 6. I have 5 pi over 6. And then I have 3 pi over 2. So these are your three answers if I asked you to label them from 0 to 2 pi. Also note, you can go pi over 6 plus 2 pi k if you want to list all answers, 5 pi over 6 plus 2 pi k, and 3 pi over 2 plus 2 pi k. But because there's a pattern here, there's another potential way that you can draw this. So I want to kind of throw that out at you real quick. So you got pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7, 8, 9 pi over 6. So if I am trying to count by this 3 pi over 2 is actually 9 pi over 6. Now notice how these angles change as I go along the unit circle. It looks like I'm adding to my numerator 4 each time. So I'm going plus 4 pi over 6 or 2 pi over 3. The gap between each angle is 2 pi over 3 or 120 degrees. Now you kind of look at that and you see that does look like it's about 120 degrees. And if you cut 360 into 3 equal pieces, that's what you're going to get. You're going to get 120, 120, and 120. So it does kind of fit. It does kind of make sense. So again, you can kind of see that pattern. You can see that there's some sort of pattern going on here. And that pattern is the answers differ by 120 degrees. So you can have an answer like this. Pi over 6 plus 2 pi over 3 times k. Again, if it's a short answer, I don't really care. I'll take all three. But again, multiple choice, if you see that answer, I don't want you to not know it's there. So the nice part about this, if these shorter answers with the patterns and things like that, you don't necessarily have to see it unless it's a multiple choice. And then even then, sometimes you see the answer, so you can kind of be like, oh wait, yeah, that is differing by 2 pi over 3, because you will recognize the pi over 6. You're definitely going to see that. You should know that that's one of your answers. And once you know that, you can kind of look and see, well, does that differ by 2 pi over 3? And you can check. And if it checks out, then you got your answer. So just understand that if there's a pattern, then we can write our answer in a little bit shorter. Like instead of 3 different equations, we can use 1 equation. Okay, and you kind of see this is the last example. So lastly, we have solving by squaring. So if I was going to solve by squaring, this involves you hopefully knowing some trig identities. That's definitely going to help here. If not, if you don't know your trig identities, well, I mean, that's it's going to be a problem. We definitely, like I said, need to know those identities, and they're going to get used here. So I try to make a point of knowing your identities for cosecant, cotangent, and tangent, and all those things, and that's what's going to happen here. So right now, solving this would be kind of a pain. If you really tried solving this without using any identities, you may notice it's really hard to isolate your radicals. Not your radicals, I'm sorry, your trig functions. That's going to be kind of a pain. But we can simplify this if we used our trig identities. So that's what I'm going to end up doing on this, is I'm going to use those identities. So I'm going to add, actually I'll use a different color here. To set up my trig identity, I'm going to add cotangent to both sides. And I'll explain why in just a second. If you don't remember your identities enough, hopefully you do. But this is going to be cotangent x plus 1. Now if you remember your identities, here's what I'm thinking right now. I know cotangent squared x plus 1 is equal to cosecant squared x. So I kind of set it up. And it's the same thing, but it's just not, as you can see, squared. But now I can square it. I have that opportunity. This is an equation. I can do whatever I want to one side of an equation, as long as I do it to the other side of the equation. So I'm squaring both sides. That's going to give me cosecant squared x. And this guy is going to now be cotangent x plus 1, and then cotangent x plus 1. So I'm going to go ahead and FOIL that one out. So this gives me cotangent squared x plus 2 cotangent x plus 1. So at this point, I have the opportunity to rewrite everything in terms of cotangent, which I couldn't really necessarily do before. I had the option of maybe changing everything to sine and cosine, but I would still have two trig functions, and that would have been an issue. But now I can write this all in terms of one trig function because I use my trig identities. So at this point, I'm going to write cosecant squared as cotangent squared plus 1. Cotangent squared x, don't forget that. And you'll see this really simplifies quite nice because the cotangent squares are going to cancel and the 1's are going to cancel. So you're going to get 0 equals 2 cotangent x, and if you divide both sides by 2, you get 0 equals cotangent x. So this really simplified quite nice, actually. So I'm going to go ahead and now look at my unit circle, and I want to know when does cotangent equal 0. So you kind of look at the unit circle and understand again cotangent. If you don't remember cotangent x, you better remember this one, but it's cosine x over sine x. So it's your x value divided by your y value. So I want to look and see when is my x value equal to 0, which is going to occur at these 2 points. So if you're looking at your unit circle, I got those 2 points. And again, if I wanted my answer to list my answer out from 0 to 2 pi, our answers are going to be pi over 2, which is at 0, 1, and 3 pi over 2. So those are those answers from 0 to 2 pi. The other answers, if I want to list them all the way out, I'm not going to circle that yet. Actually, you'll see why in a second. The other answers, I can go x equals, and actually before I get to that other one, because the other thing I wanted to mention, let me talk about something real quick before I wrap this up. So understand what I just did is I squared both sides of this equation, and whenever you square both sides of an equation, what ends up occurring potentially is you get a situation where you may have extraneous solutions. An extraneous solution is a solution that works in the equation that you created by squaring both sides, but it doesn't necessarily work in the original equation. Some basic examples is something like this. If I had like x equals 4. So if you go x equals 4 and you square both sides, again right now x is 4. That's the answer. You square both sides, you get x squared equals 16. And then as you solve, you're factoring, you're breaking things down. And this is the most basic form of that. So I say I square rooted both sides. Now I get plus or minus 4. So now I started with 4. I ended up with plus or minus 4. So if you ended up plugging that back in to the original equation of x equals 4, so this is the equation. If you plug in 4, it works. If you plug in negative 4, it doesn't work, and you get an extraneous solution. So this occurs anytime you have to square both sides. You get the potential of this occurring. Now, it doesn't mean you're going to have an extraneous solution. All I'm saying is you need to make sure you double check. So this involves, again, checking and understanding how to evaluate your trig functions. So at this point, I'm going to go ahead and check for extraneous solutions. It only happens in this scenario. So if you're not squaring both sides, don't worry about doing this step. This is particular to squaring both sides whenever you do that. So the original equation was cosecant x, and then I had minus cotangent x equals 1. And again, I'm just going to go ahead and plug in those answers and just basically see what I get here. Okay. Now, when you plug this in, you're going to get cosecant of pi over 2 minus cotangent of pi over 2. And again, I want to see, does that equal 1? So I'm going to zoom in on this real quick as I do it. So cosecant, that is 1 over sine pi over 2. And cotangent is cosine pi over 2. divided by sine pi over 2. So again, sine pi over 2, if you know your unit circle, literally we're just going up to this point 0, 1. Sine's your y value, so that's going to be 1 over 1. And cosine over sine is your x value divided by your y value, which is 0 over 1. I don't know why I put equals. And again, does that equal 1? Well, 1 minus 0 does equal 1, so this answer does check out. So we are good. And because if you understand the period for cotangent is pi, so I don't need to check this second answer because it's going to be the same thing because it's along the period. But if I had like another unique answer, like I had an answer out here or something like that, notice these aren't within the same period. I would need to check those. And again, if you're ever not sure, should I check, should I not check, check. But this one is going to check out, so these are our answers. We are good. So from 0 to 2 pi, those are my solutions. And if I wanted to write this out, I can go x equals pi over 2 plus pi k. As you see, it does repeat every pi, and that's the period for cotangent anyway. So these are all the scenarios that you can possibly see in terms of solving. So make sure you are comfortable with each one, and you know, as you work through these, you kind of get used to recognizing it right away. But again, we'll have some time to practice these. Hopefully have some time here in class to do it, and we'll have some time to go over questions and whatnot during our block period this week. So go ahead and get started on this. By the way, your assignment, go on eCampus. There's a assignment called solving trig equations.pdf. What you're going to do is you're going to work through both sets. There's 2 sets of 10. So you'll work through both those sets. The only difference between them is one is all in terms of degrees and the other one is all in terms of radians. So go ahead and give that a shot, and again, I will see you guys during block periods.